Assalamualaikum and good morning everyone. My name is Ashimah binti Kana and currently a final year student AS 244 Biomolecular Science program at University Technology Mara. So today I am pleased to present my final year project research on metabolomic profiling for human milk among breastfeeding mothers with maternal stress. This study is supervised by Puan Siti Nofahana Mama Idris. So let's delve into the detail of this important research. So the background study of this project is human milk is a dynamic secretion providing essential nutrients and bioactive metabolite influenced by factors like maternal genotype, ethnicity, age, BMI, and diet. It actively regulates infant immune and cognitive development, impacting growth and disease risk. Perinatal psychopathology in over 25% of mothers affect milk component, which is lipid hormone and immune factor, potentially impacting infant neurodevelopment and long-term health. Cortisol in human milk correlates with maternal plasma levels and can act as a signaling mechanism affecting infant behavior and brain development. So in this slide, we will discuss about the problem statement. The study aims to explore the difference in the metabolomic profile of human milk between mother experiencing high level of stress and those with low or no stress. So the next problem statement is the study seeks to identify which specific metabolites are most significantly altered due to maternal stress and to investigate their potential roles in infant growth and development. There are two objectives on this study. Our first objective is to identify the metabolic component present in human milk from breastfeeding mother experiencing very level of stress. By using advanced metabolomic profiling technique, we aim to comprehensively analyze the range of metabolites in the milk sample. The second objective is to compare the metabolic profile between milk from stressed mother and non-stressed mother who will serve as control. By contrasting this profile, we aim to point the specific metabolites that are significantly altered due to maternal stress. So let's move to methodology part. As you can see here, our first method starts with data collection from mothers. We start by administering the DAS21 test to assess the stress level in participating mother through Google Form from the QR code given on the flyer and poster. From that information gained from respondents, we use to recruit participants who meet specific inclusion and exclusion criteria. The next method is breast milk sample collection. The milk is collected using a breast pump stored in plastic tubes and then frozen at -20 degrees. Next is sample preparation. The milk sample undergo 2 rounds of centrifugation to obtain skim milk for further analysis. The proton nuclear magnetic resonance NMR analysis is performed on the sample. The sample are mixed with a chloroform or methanol mixture, vortex, and centrifuge. The aqueous fraction is dry and reconstituted in a phosphate buffer solution for NMR analysis. The next method is the most important method in this study, which is NMR spectroscopy. We conduct NMR spectroscopy using a Bruker Advanced 3600 spectrometer at 298K with a 5 mm1 HTXL probe. The standard one-dimensional nuclear over Hauser enhancement spectroscopy pulse sequence was used. The last method is data analysis. The experiment was conducted at the Institute of Research PTM Puncak Alam with a sample size of 12 subjects, which is a 6 subject per group. NMR spectra were processed using Nova version 15.0 and correct for chemical shift misalignment. So this slide presents result and discussion. As you can see here, the table shows the DAS test score participating of 6 mothers. In the study, 6 participants were evaluating using the DAS21 test to assess their level of depression, anxiety, and stress. The participants were divided into 2 categories, which is 3 mothers experiencing high level of stress, 3 mothers not experiencing stress. So as you can see here, this figure display the comparison stack NMR spectra of human milk from stressed mother, which is an A01 and A02 and A05, and non-stressed mother and A03 and A04 and an A06. The key finding found in this NMR spectra is leucine, which is 0.595 ppm. Show more prominent in stressed mother, indicating higher protein synthesis demand or stress-induced metabolic changes. The next metabolite found in this peak is 3-hydroxybutyrate, which is 1.17 ppm. Show clear peaks in stressed mother's milk, suggesting elevated ketone bodies and altered energy metabolism. The next metabolite found is alanine, which is 1.47 ppm. Show higher concentration in stressed mother, pointing to changes in glucose metabolism. The next metabolite found is glutamate, which is 2.34 ppm, show noticeable peaks in stressed mother, indicating alteration in neurotransmitter level and amino acid metabolism. The next metabolite found is 3.03 ppm, present in stressed mother milk. The next metabolite found is lactose, which 3.75 ppm, show more intense peak in stressed mother, reflecting difference in milk composition affecting infant nutrition. So last metabolite found is myoinositol, which is 4.05 ppm. So as you can see here, the table shown that specific metabolite present in stressed mother and that's absent or absent in non-stressed mother, and their potential roles based on chemical shift metabolite from previous study as a reference. So as you can see here, leucine shows 0.90 to 1 ppm, As we know, leucine is an essential amino acid critical for protein synthesis and metabolic function. In the context of maternal stress, elevated cortisol levels have been linked to increased leucine concentration in human milk. Leucine plays a vital role in stimulating muscle, protein synthesis, and overall growth. Its higher presence in the milk of stressed mother could indicate an adaptive mechanism to support the infant growth, metabolism, and growth during periods of maternal stress. So the next metabolite is 3-hydroxybutyrate. The range of chemical shift is 1.15 to 1.20 ppm. So as we know, 3-hydroxybutyrate is a ketone body produced during fatty acid breakdown and is crucial for energy production, especially during fasting or low carbohydrate intake. Increased level of 3-hydroxybutyrate in the milk of stressed mothers suggests enhanced fatty acids mobilization due to cortisol. And for infants, these metabolites serve as an alternative energy sources, which might be particularly important during times when glucose availability is limited. However, prolonged exposure to elevated ketones body could have implications for the infant's metabolic health. The next metabolite is alanine. The range chemical shift is 1.45 to 1.50 ppm. Alanine is involved in glucose metabolism and energy production. The higher concentration of alanine in the milk of stressed mother may reflect alteration in amino acid metabolism induced by stress. Alanine can be converted to glucose in the liver, providing a quick energy sources for the infant. These metabolites increased present in milk will help maintain the infant's energy balance during maternal stress. The next metabolite is glutamate, which is a chemical shift range is 2.30 to 2.35 ppm. Glutamate is a key neurotransmitter that plays a critical role in brain function and development. Elevated glutamate levels in the milk of stressed mother could influence the neurodevelopment of infants. While glutamate is essential for proper brain function, its excessive amount could potentially lead to exotoxicity, highlighting the need for a balanced concentration. Our findings indicate that these amino acids were present in milk of both stressed and non-stressed mothers, but their concentration were lower in milk from stressed mother. This might be decreased due to heightened metabolic demand under stress, diverting this amino acid from milk synthesis to other physiological functions. The lower availability in human milk could affect the infant's ability to maintain optimal neurotransmitter function. So another metabolite found in human milk stressed mother is creatinine, which its chemical range is 3 to 3.05 ppm. Creatinine is a breakdown product of creatinine phosphate in muscle. Higher level of creatinine in the milk of stressed mothers suggests increased muscle protein breakdown or altered muscle function due to cortisol. For infants, creatinine in milk could indicate the availability of precursor for energy production and muscle development. Our analysis showed a decrease in creatinine level in the milk of stressed mother compared to non-stressed mother. This reduction might impair the infant's ability to metabolize fatty acid efficiently, impacting energy production and growth. The most metabolite found in human milk, lactose, also found in human milk in stressed mother. The chemical shift range for lactose is 3.70 to 3.80 ppm. As we know, lactose is the primary carbohydrate in human milk, crucial for providing energy to infants. Variation in lactose level due to maternal stress could impact the calorie intake and energy provision for the infants. So the last metabolite found in human milk stressed mother is myoinositol. The chemical shift range of myoinositol is 4 to 4.10 ppm. Myoinositol is involved in cell signaling and growth. Elevated levels of myoinositol in the milk of stressed mother may influence cellular process and development in infants. This metabolite's role in brain development and function make it particularly important for the neurodevelopment of breastfed infants. It is important to note that the DAS test is used to essential maternal stress is a self-perceived or self-diagnosed tool and may not always accurately reflect the true stress level of the mother. Some mother with low DAS test score might still experience significant stress in real life, which could affect milk composition. Therefore, the association between cortisol and lipid metabolites such as butyrate and acetic may still be relevant even in mother who score low on the DAS test. So the conclusion from this study is this study successfully identified significant changes in specific metabolite associated with maternal stress in human milk. Elevated cortisol level in stressed mother were linked to increased concentration of metabolite like leucine, 3-hydroxybutyrate, alanine, glutamate, creatinine, lactose, and myoinositol. This alteration suggests that stress impact protein metabolism, energy supply, and neurodevelopmental aspect in infants. So the recommendation that we can learn from this study is implement long-term study to monitor variation in milk composition over time. By use comprehensive stress assessment tools including biochemical markers and self-reported measures. This could be useful for further study. For the second recommendation is develop technology for comprehensive metabolite analysis in human milk by invest in advanced tool for efficient and comprehensive milk metabolite analysis. For example, high-throughput metabolomic platform and advanced analytical technique can improve the accuracy and efficiency of metabolic detection and quantification. Developing and utilizing more accurate tests to assess emotional, physiological, and hormonal changes that affect metabolites in the body is essential. So that's all I can conclude from this study, and thank you for hearing my presentation and for your time. And that's all from me. Thank you.